All right, this is a video for geometry on isosceles and equilateral triangles. We'll start off with an introduction with a theorem that we'll look at, and then we'll do a few different solved examples. So a reminder that an isosceles triangle is a triangle with two congruent sides. So here's an example of one right here. The isosceles triangle theorem that we'll be looking at today says that if we know a triangle is isosceles, then we also can conclude that that triangle's base angles are congruent. Okay, so that's a really handy theorem. It's pretty intuitive, I believe, as well. So if we know that these two sides are congruent, then the base angles must be congruent as well. I want to talk about the converse of that theorem. As a quick reminder, if we haven't talked about it lately, the converse of a conditional statement, if we have a conditional statement, if A is true, then B must be true. The converse of that statement is if B must be true, then A must be true. Okay, so you can think of it as flipping the order of the conditional statement. So the converse of this isosceles triangle theorem is also true, meaning if we know that two angles are congruent in a triangle, then we know that the triangle must be isosceles. So I'm actually going to draw this arrow here as a double-headed arrow to show that that conditional statement can operate in both directions. Okay, so let's apply that here with a little bit of an abstract problem, actually, where I'm giving you a couple overlapping triangles and I'm asking you to think about what can we conclude from these triangles, from the information that's given. Let's look at the small triangle ADE first. We're told that it's isosceles. So let's use the isosceles triangle theorem to conclude that these base angles must be congruent. So I'll label that. So this angle must be the same as that angle. Okay. We're also given some additional information here. We are given some information about these two angles in the larger triangle ABC. Those marks also show that angle A is congruent to angle C. So what else can we conclude? We can conclude that the large triangle, because it has two congruent angles, the large triangle must be isosceles. So let me get caught up with my labeling a little bit here. So these angles were given as congruent. We initially determined that those two base angles are congruent. And now we can also determine that these two highlighted sides are congruent. Okay, so that's an isosceles triangle. And I think there's actually one more interesting thing we can conclude here. It looks like these two segments appear to be intersected by a transversal, the transversal AC, and it looks like we have congruent corresponding angles. So I'm going to additionally conclude that DE is parallel to BC. We can conclude that as well. So what else did we say? We said angle A is congruent to angle DEA, and we also said that triangle ABC is isosceles. Maybe you can conclude some more information from that as well, but we'll move on. I'm going to give you three more isosceles triangles theorems, or theorems related to isosceles triangles. The first one is called the vertex angle bisector theorem. So once again, we are given an isosceles triangle. If we know that is true, what can we conclude? We can conclude that the vertex angle bisector, so a line segment that bisects that vertex angle, will be the perpendicular bisector of the base. Okay? So the givens are if a triangle is isosceles, and if we know that we have a vertex angle bisector, then we can conclude that we also have a perpendicular bisector to the base. That's a little bit more of a complex one. The next two are a little bit more straightforward, and they refer to equilateral triangles. If we know a triangle is equilateral, then we can conclude that it is equiangular, that all the angles are the same, which is also useful if we know that the sum of the angles in a triangle is 180. We can therefore conclude that each angle is 60 degrees. And conversely, if we know we have an equiangular triangle, we can conclude that all those sides must be the same. The triangle must be equilateral. So these two are converses of each other. All right, let's do a couple more solved examples. First one, we have triangle DEF over on the left. We know the vertex angle is 30 degrees. We know it's isosceles. We are looking for angle X. So since we know it's isosceles, we can say that this is angle X as well. Or angle F has a measure of X degrees, to be precise. So we can write out an equation. We can say that 30 plus 2x has to equal the triangle sum of 180 degrees. 2x therefore has to be 150. So it looks like x will have a measure of 75 degrees. We could always test that by doing 75 plus 75 plus 30 to see if we get 180. Let's look at the one on the right. A little bit more complex because we have three triangles involved, two smaller triangles and then one large triangle. It looks like we're given an isosceles triangle. It also looks like we have an angle bisector to the vertex angle. This triangle is upside down from what you typically see an isosceles triangle drawn as, but that's all right. So let's try to figure some stuff out. So I can tell right away that this will be 42 degrees because that's the other base angle of the isosceles triangle. And I can also tell that this would be x degrees because those are listed as congruent angles. So I can write out another equation. I can say 42 plus 42 plus 2x's equals 180 degrees. So just to be clear, we're working with a large triangle. We can solve solve this equation. 84 plus 2x is 180 degrees. Let's subtract 84 from both sides. So 2x is going to be 96. And then just divide by 2. And we're going to get x is equal to 48 degrees. Another way to have done that, just by the way, I'll just talk you through it. I won't actually do it though. If we were to just work with this smaller triangle, since we're working with an angle bisector to the vertex angle, we would know that we have a right angle that we're working with because it's a perpendicular bisector. And then we just need the 42 plus the 90 of the right angle plus the x has to equal 180. So another way of thinking about that problem. Last one, and this is a fun one. I like doing this one. What we're being told here is that the measure of one angle of an isosceles triangle is 23 degrees. Determine the other angles. Okay. What makes this tricky, and I encourage you to maybe pause this video and try this on your own first and see if you encounter the trickiness on your own. But what makes this tricky is we don't know if the 23 degrees is a base angle or a vertex angle. Okay, so I'm going to draw a triangle, and it's not going to be to scale. I'm not going to worry about making a triangle to scale right here. I just want to have a little bit of a visual. Let's assume the vertex angle is 23 degrees. Then we have two congruent base angles, each of which are equal to x. So we can write now an equation and say 23 plus 2x is 180. Separately though, and let me redraw my triangle, perhaps the base angle was 23 degrees, which means the other base angle would also be 23, and then the vertex angle, and I'll call it y in this case, would be our unknown. So we can say 23 times 2 plus y equals 180. So we have two possibilities. We're going to get two answers eventually, and let's solve them both. So let's work with the top equation first, subtract 23 from both sides. And so we have 2x is equal to 157. And then we can divide by 2, and we get x is equal to 78.5. So that's one possible answer. Okay, and just to be clear, that triangle would have a 23 a 78.5 and another 78.5 angle in it. Okay, let's do the second possibility where the 23 was the base angle. Let's simplify. 23 times 2 is 46 plus y is 180. We'll subtract 46 from both sides and we get y equals 134. And then to be clear, our angles here would be 134, 23, and 23. So both of those are valid answers. The trick here is to realize that there are two possible sets of answers. So isosceles triangles, congruent sides leading to congruent base angles. We got through it, and that's a great place to stop.